Hello and welcome to the course Basics of Experimental Design for Cognitive Psychology. I am R. Kwarma from the Department of Cognitive Science at IIT Kanpur. In this week, we are basically having a brief historical background of the scientific method, and then we'll eventually go on to the nitty-gritties of experimental method in cognitive psychology. Now, in the last lecture, we talked about a little bit about the logical positivism movement as one of the fundamental movements that wonders about the generation of scientific knowledge. And we stopped that lecture at some place around when we were talking about the principles of scientific principles of generation of scientific knowledge as proposed by the logical positivists. One of the interesting aspects that we discovered therein was this idea of verification, observation and induction. So, observation, induction and verification as the three pillars of scientific knowledge. Now, we looked at that and we concluded with this idea that verification, because it is physically tenable, it is logically impossible to verify all the knowledge that we have generated. Verification probably cannot be the fundamental basis of scientific knowledge in that sense. So, we will move on, we will look at other ways in which scientific knowledge can be generated and interpreted and so on. Now, an alternative to the shortcomings of the positivist stance, which basically held observation, induction and verification, was observed by this gentleman called Karl Popper. Karl Popper basically published one of his most important works, Logik der Forschung, the logic of scientific discovery, in 1934, and he provided us some of the most seminal and the most fundamental ideas about the generation of scientific knowledge, which probably guide the scientific discipline even now. Now, one of the central ideas that was proposed by Popper was this idea that falsification instead of verification will be the more appropriate method for generation of scientific inquiry, for generation of scientific knowledge. Popper emphasized the importance of having theories of scientific thinking, because theories allow this weaving of observable and verifiable facts into a framework, and it also allow a means to question the presented explanation of these facts. Remember, we were talking about the fact of the fact that both inductive and deductive reasoning are based on some observations. Now, unless you have a theory, unless you have a framework to interpret that observation within, all of these observations will seem as isolated, disconnected, unorganized facts. If you have only these, it is difficult to build knowledge. These are all isolated observations that will stand by themselves, and we will have no means to connect them. We will have no means. We will be no closer to understanding any given phenomena, because we don't have a theory of how that particular phenomena functions, or how these particular findings can be stitched together. So, in that sense, Popper actually says it is very important for scientists to have theories, and these theories will allow us this framework to stitch together particular observations, accept some of them because they sort of fall within the ambit of the predictions that a theory generates, and leave out some of them which basically do not fall within this ambit. For instance, Popper dwelt on the difference between Freudian psychoanalysis and physics. More specifically, around that time, both of these were dominant schools of thought, and both aimed to be part of scientific knowledge. Studies in physics typically were aimed at the suspected weaknesses of these theories, at identifying the suspected weaknesses of these theories. Say, for example, Newton's laws of motions, or Einstein's laws of general relativity, things like that. Most of the experiments were being carried out to test and to sort of falsify these theories by aiming at the weaknesses. On the other hand, what was interestingly happening in psychology, or broadly psychoanalysis, was that people were engaged more in finding confirming evidence rather than working at refuting these theories. So what both of these disciplines found was that while the theories in physics got stronger and stronger because they could not be, let's say, falsified, or some were falsified and new theories emerged in their place. In psychoanalysis, what was happening in psychology, what was happening was that psychologists in the psychoanalytic tradition were finding more and more confirming and corroborating evidence that supported psychoanalysis as a preferred method. It's only later that people reviewed these findings and said that they cannot be really treated as bona fide scientific theories. So Popper pointed out that this latter approach of targeting weaknesses and testing whether a particular theory can be falsified is more important. He said that this approach of finding corroborating evidence is basically the one that also is followed by religions and sects and so on, and is basically more characterized by knowledge based on belief and faith and so on, and not scientific knowledge. So Popper points out that what discriminates scientific from non-scientific theories were the fact that the scientific theories are indeed falsifiable. What do we mean by falsifiability? Falsifiability basically indicates that the statements can be falsified, statements within a given theory can be falsified as they offer precise, clear predictions that can be tested and found to be true or untrue. For example, if I have a statement like this, say for example, if I say that it is colder in January than in March. Now, it's very easy to falsify this statement. You basically measure the temperatures in the month of January, measure the temperatures in the month of March, and if you find out the temperatures in January are not colder than in March, you can falsify it. On the other hand, you can actually find supporting evidence for this as well, but that is not found to be that is not deemed to be the best way of establishing this as a scientific theory or a scientific fact. So Popper emphasized on the need of that proponents of scientific theory should put their ideas to test effectively by actually trying to find instances where these theories will not work. Okay, so if you have a theory about something that, okay, this is how things work, you have to find out and be able to specify situations A, B and C where this thing will not work. Within the same tradition, Popper puts forward the hypothetico-deductive model. What is this model? According to this model, scientific progress involves a combination of both inductive and deductive reasoning. We start from observations. For example, one follows inductive reasoning, making these observations, and then builds up interpretation or a theory for a given phenomena. So you observe, say for example, you observe that people are wearing, more winter clothes in January. People are wearing, they are switching on heaters in January, this and that, and so you observe a bunch of things that basically say, okay, this is probably what is happening. On the basis of these observations, you say, okay, it seems that January is colder than March, something like that. You observe less of people switching on heaters and wearing winter clothes in March. You make these observations, you basically come up with an interpretation that, okay, it seems that January is much colder than March, something like that. It's probably not the best example, but let's work with this. Now, to check the correctness of this interpretation that, let's say, January is colder than March, the researcher would employ deductive reasoning to generate testable predictions. So how do I go about this now? We generate testable predictions that, okay, the average temperature in the first week of January or the first week of March will be, so average temperature in first week of January will be lower than that of first week of March by so many degrees, something like that. Okay, now this is something that can be verified by experiments or by data collection. You just have to take measurements, maybe at different places, maybe at the same place and so on. You have this data, and this data will tell you whether whatever I am interpreting is correct or not correct. So the conducted experiments then provide new observations for further theorizing and generating newer predictions and so on. Now, an example of this, probably a better one than I was using, is presented by Brisbane and Russell, which is about, say for example, when Louis Pasteur discovered the source or the reason of why wine, milk and beer were getting soured over time. So using inductive reasoning, Pasteur concluded that this might be happening due to the microorganisms present or introduced in these liquids by the environment. So he said once these liquids, say for example wine, beer or even milk, are introduced to the environment, they are kept in uncovered containers, the air introduces microorganisms in these environment, which causes the souring of these liquids. So he hypothesizes that if his interpretation is correct, that there are microorganisms in these liquids introduced by the air, then he should be able to prevent this souring by putting a filter between the liquid and the air in which these liquids are, and the air in which these liquids are kept. You basically create a filter. The filter prevents microorganisms from the air entering the liquid. Indeed, Pasteur was able to demonstrate that an air filter actually prevented the souring of wine and beer, which basically verifies the fact, which basically tells us that yes, probably the microorganisms were the actual cause of this souring. This could not be obviously done for milk because milk already contains some of these microorganisms. So later he discovers that milk actually needs to be boiled to kill those microorganisms that are already present therein, and hence that will be the way to prevent souring of milk. Popper stressed on the fact that hypothesis testing therefore should be directed at falsifying a theory rather than finding confirming evidence, because if the researchers fail at several attempts at rejecting a theory, that constitutes a much stronger evidence rather than any number of confirming evidence. Remember, we were saying in the previous lecture that if you have a theory that all swans are white, even if one swan that is not white basically rejects this theory. So you can find one swan, 10 swan, 1,000 swans, million swans that are all white and use that as corroborating evidence for your theory that all swans are white. But even if somebody is able to present one black swan, it actually refutes this theory completely. So instead of finding confirming evidence, Popper said that science would progress better if we focus on finding that black swan. If we are not able to find that black swan after repeated attempts, then we have better grounds to assume that okay, all swans are white is an acceptable theory. So Popper proposed, following the same thing, that scientists should generate bold theories in form of speculative and tentative conjectures, and then go ahead with rigorously testing them on the basis of experimentation and observation. So you come up with a particular theory and you work with in what conditions this will not work. Now, as theories are not generated, as scientific theories typically are not generated with any guarantee of being correct, it is perfectly plausible that theories typically will turn out to be wrong every once in a while, even when they initially seemed to be in line with the collected evidence. So every once in a while it basically allows scope for theories to be modified, corrected, or even be junked. Now, this approach highlights an important aspect about theories. For instance, the scientists are never completely sure about the correctness of their theories. You've seen in physical sciences, for example, several well accepted theories are after a number of years being rejected or found to be untrue. In psychology, for example, Piaget's theory of cognitive development was found to be not true by more recent researchers who said that, say for example, the timeline of object permanence is not within that ambit of what Piaget had initially suggested. In fact, the confidence of scientists in their theories is only as much is basically directly proportional to the degree to which a particular theory survives the attempts at falsification. So the number of tests of falsification a theory survives, the more confident a scientist can be about his or her theory. So in essence, what can we conclude from this? Scientific theories can actually be proven to be false, but they are true only to the extent to which they have survived these attempts at falsification. Now, following from this stance, progress in science can actually be seen as a process of trial and error. You come up with something, you keep on trying to falsify it. You falsify it sometimes, you're not able to falsify it sometimes. So it's almost like a a process of trial and error, where several possible explanations of a phenomena may be offered, but only those explanations will survive that will survive this test of falsification. The strongest and the fittest explanations will only continue and will basically form the body of scientific knowledge, as opposed to explanations that are weak conjectures that are proven to be false by the initial tests or initial attempts at falsification. Also, falsification ensures that scientists are less likely to stick to wrong opinions more than common people. For example, common people or commonplace knowledge is typically governed by belief and faith in opinions which are not extremely well scrutinized, which are not tested all the time. And because they are not tested, because we are not looking for, see, there are aspects like, and we are aware of things like cognitive bias maybe, or confirmation bias actually. Confirmation bias is a tendency of people to look for confirming evidence rather than look for refuting evidence, because our typical common sense reasoning is afflicted by things like confirmation bias. Scientists' knowledge is considered stronger because they are establishing and building on scientific knowledge on the basis of falsification, whereas we as common people are building upon our knowledge on the basis of confirming evidence. So science therefore is more prone to learning from its mistakes. However, again, it must be noted that not all scientific advice or all scientific knowledge can be considered with a lot of confidence unless it has been tested, unless it has passed the test of falsification. Now, is falsification a binary? Is something falsified and then junked at the same time, or say for example there can be degrees of falsifiability in these scientific theories? Now, an interesting caveat that also Popper discusses is that different scientific statements may lend themselves to different degrees of falsifiability. For example, at least as what Popper says, that the degree to which a scientific theory or a statement exposes itself to testing and falsification, that determines how scientific that theory can be deemed to be. For instance, look at these two statements. Wine sours because of microorganisms. Wine sours because of bacteria coming from the air. Now here both are very similar statements, but in the second one the statement is a little bit more specific. We have also specified the type of microorganism that may be responsible for souring of the wine. Now the second statement, because of being more specific, is more prone to the test of falsification, and it lends itself to this test of falsification, is therefore going to be deemed to be more scientific. The first theory, we are just saying microorganisms. Now if you don't find bacteria, you can say, oh, it were viruses. If you don't find viruses, you can say, oh, it is another class of microorganisms, and so on and so on. All right. So the more specific a theory is, the more testable statements it will generate, and the more testable statements it generates, it exposes itself to falsifiability, and in that process becomes more scientifically valid theory. All right. So also there is an aspect about the scope of a given scientific theory. Now according to Popper, the more facts that are covered within a scientific theory make a given theory more scientific. So any theory that we are talking about should not explain facts or phenomena selectively. It should aim to explain more and more, and as many of the facts, observed facts, that are explained within this particular framework. So case in point can be, say for example, Einstein's a test of Einstein's theory of relativity by this gentleman called Eddington. Now Einstein had predicted that rays of light would bend as they passed close to a massive object. Now Eddington wanted to test this, so he decided to make use of a solar eclipse in the year 1919, and he basically sent expeditions to two different places where the observations, the chances were to get best observations. One expedition was sent to the island of Principe along the west coast, and one was sent to northern Brazil. Now each expedition was asked to take pictures of the sky during the eclipse, and also on a night where the stars were at the same position relative to the earth, so that the observations are comparable. Now The results obtained from this were actually less clear cut than what Eddington had hoped for, but they still were able to convince nearly all the researchers involved in this that the data typically agreed with Einstein's predictions and was significantly different from what was basically predicted by Newtonian physics. So on the basis of collecting these observations, Eddington was able to test and confirm the theories offered by Einstein relative to the theory offered by Newton. For example, just to sort of give you a more detailed peek, there was a significant difference between the perceived location of stars during the eclipse and the perceived location without the interfering sun. Also, the magnitude of the deviation was in line with the measurement error that was predicted by Einstein's theory and not by Newton's theory. So Popper basically says this could be touted as one of the best examples of science at work, an extremely falsifiable theory because it gives very specific and precise predictions was being put to test. There were hundreds of, see, if you did not have a theory in the beginning, if these observations were being randomly made, then there could be hundreds of plausible reasons to expect no difference at all in the perceived locations of stars during the eclipse and at a time when the eclipse was not happening. There was only one reason that was predicted by Einstein's theory that would basically predict this deviation, and because it was found, these predictions fitted very well and basically were used to confirm the theory offered by Einstein and the calculations. Now, degree of falsification, scope of falsification, but again this idea of how falsifiable is something, or do we junk the theory at the first test of falsification, it fails. Now, while Popper offers this very sound method of the progress of science, researchers have wondered about the fact that whether a theory should be rejected immediately and completely upon failing the first test of falsification. Researchers needed to investigate whether the data were sound, because see, researchers typically are sort of clingy towards the theory that they come up with, and they don't want to reject the broad theory in the first place. Okay, so what do? They start with asking questions about the veracity of the data, veracity of the observation, veracity of the method of data collection, and basically because they don't want to reject a given theory based on flawed data. Also, if they were convinced of the soundness of evidence, they will typically try and find ways in which this new data can be accommodated by by within the same theory without changing it so much. So it seems therefore a more pragmatic approach that one can adapt, or that we modify the theory a little bit to see if the findings can be accommodated within the same theory rather than throwing away the theory altogether. So an example basically that is cited by Brisbane and Russell is that modification of the existing theory to accommodate the position of Uranus in the planetary system. For example, as per extant observations in the 19th century, it gradually became undeniable that Uranus' path actually deviated too much from Newton's laws to be acceptable. So either you throw away the Newton's laws, or you basically say that there is probably some issue that is coming up in the calculation of the the path of the Uranus around the sun. Going by falsification alone, scientists could have given up their theory and looked for an alternate explanation. However, Leverrier in France and Adams in UK actually proposed that Newton's laws could be saved if we found somehow that there is another planet in the neighborhood of Uranus that is influencing its orbit. On the basis of these predictions, astronomers started to look for this probable planet, probable heavenly body, and they started to calculate the whereabouts of this new planet and its approximate size and so on. These efforts eventually led to the discovery of the planet Neptune and basically allowed for a way to reconcile Newton's laws with the orbiting path of Uranus. So you can basically see it's not probably the best idea to first to throw away, junk away a particular theory on the first test of falsification, the grounds of falsification must be verified, in great detail. So this evidence basically suggests that a given theory can be modified so that it is not any longer contradicted by the available empirical evidence. Even Popper eventually agreed to this, that scientists should not give up theories too easily and first test the tenacity of the given theories through successive and iterative tests. So multiple tests of falsification. However, interestingly, he points out that the modifications to a given theory should not in any condition make the theory less falsifiable. So he was actually against ad hoc modifications. Modifications that say, for example, you come across the first test of falsification that your theory does not do well against, you say, okay, maybe we modify this particular aspect here and it will work. Then another modification, then another modification. If we are making random ad hoc modifications that are making the theory less and less falsifiable, that is bringing in vagueness in the theory, then these modifications are what Popper guards us against. Now, so this is so far. Now, how do we move from here? Is basically something that is offered by Thomas Kuhn. Thomas Kuhn was an American physicist who eventually became interested in the history and philosophy of science, and he takes the discussion forward about forming scientific theories and verifying and scrutinizing these scientific theories through one of his famous works, The Structure of Scientific Revolutions. All right. So Kuhn emphasized that all observations and theoretical concepts basically are to a certain extent influenced by the language of this adopted theory or the adopted conjecture, and that typically scientific disciplines are driven by prevailing traditions and conventions within their disciplines, and in some sense, if you deviate from these conventions, it invites isolation and ostracization and so on. So Kuhn basically provides a framework that basically allows us to observe this falsification test and this exercise of falsification in more context. Let us look at that. Now, according to Thomas Kuhn, scientific progress has a structure. According to this structure, scientific knowledge progresses through a series of iterative steps. So it basically says that once at some point people are in a stage of pre-science, then goes to normal science, then there is a crisis or a revolution, something major happens here, and then eventually people come to pre-science, normal science, and so on again and again. So this is a cycle that repeats every once in several years. What is this pre-science that we are talking about? At the beginning of each scientific discipline or each scientific inquiry, researchers are typically trying to understand the phenomena through a series of ill-organized isolated facts. This happened here, this happened here, this happened there, and all of these facts are basically there, and people are trying to connect them, people are trying to make sense of them, but because we do not have a wider framework to understand this, there might be competing or contradicting explanations. There might even be disagreements about the correct methods to be followed to understand a given phenomena, to basically validate or situate the investigation. So what Kuhn offers is that there should be a general framework which allows us to organize the seemingly disconnected findings, disconnected observations, even say for example theories. So it's probably a superstructure to these theories. So this framework will inform the researchers about the intercorrelations of these various ideas, and also about some guidance about the methods that must be used to properly investigate these facts. And this framework is what Kuhn referred to as a paradigm. What is a paradigm? Simply defined, it is a set of common views about the discipline and about how the specific problems in the discipline may be approached, what kind of methods have to be followed, and what is considered valid sort of bona fide aspects of inquiry within that particular discipline. So according to Kuhn, paradigm basically specifies a bunch of things. So for example, it specifies what are the phenomena that must be studied, what are the things that must be observed and scrutinized. What questions do we ask about these phenomena? What are the more acceptable questions to be asked? How do we structure these questions? How do we structure our scientific inquiry? And also, whatever we are finding, how do the results of these scientific inquiries be interpreted? So all of this falls within this superstructure called a paradigm. Now, once a paradigm is established within a given discipline, that is where Kuhn says that we are in the phase what is called normal science. So, at any point in time, a discipline is functioning within this phase of normal science, where there are theories offered. Theories basically test particular phenomena, predict particular phenomena, test particular phenomena, and there are attempts at falsification. It all is happening within a particular wide broad framework. So within this framework, what will happen is there will be attempts at proposing theories, attempts to falsify the proposed theories, and test the overall strength of these theories. If, however, a systematic deviation is discovered between the predictions of a given theory and the observed line of findings, you can modify these theories within a given degrees of freedom, and without making fundamental changes to the core idea of a paradigm. Say, for example, in psychology, we can talk about the behaviorist paradigm of psychology, the idea that there are stimulus response associations that are the basis of understanding human behavior. There can be any number of findings. There can be, say, for example, conditions of classical conditioning, operant conditioning, this and that, and all of those findings are being viewed under the broad behaviorist idea. Now, every now and then there will be crises in any given scientific discipline. What is crisis? Basically, when you start having anomalies, initially findings will start appearing that cannot be accommodated within the existing framework or within the existing paradigm. So typically what happens is, in the beginning, these findings will be seen as anomalies which cannot be accounted for or reconciled within the given paradigm, and when this happens, basically what will happen is researchers will start questioning the validity of the findings. They'll start questioning the methods that have been used to obtain those findings, and they'll find, eventually, if nothing is working, they'll find ways of accommodating those findings without changing the paradigm. However, in some cases, these anomalies will keep on mounting up, they will keep on accumulating, and they will become more and more severe, and at some point it will become inevitable that these anomalies, that these new findings cannot be reconciled with the existing paradigm of investigation. And when this happens, you can say that yes, the discipline is in a crisis at this point. There are so many new findings that cannot be explained within the existing paradigm of, let's say, looking at human behavior. Now, when such a situation transpires, there will emerge a need for the replacement of the existing paradigm and make new predictions that can repeatedly stand the test of falsification. This particular point, this particular emergent point, has been termed as a scientific revolution, and a scientific revolution typically leads to what is called a paradigm shift. So a shift in the broad framework of how a discipline approaches a given phenomena, what are the acceptable methods, what are the acceptable ways of inquiry, etc., sort of changes. So paradigm shifts are characterized by intense scientific progress, clarifications of hitherto ill understood facts start appearing, and new ground is broken, new knowledge sort of appears, and you basically move from one broad framework to another new framework. Kuhn says that this could be the process of immense scientific excitement, unlike the everyday run-of-the-mill findings that are reported during the phase of normal science. Say, for example, during the behaviorist era, or let's say during the psychoanalytic era, or now during the cognitivist era, and within cognitivist era you have the information processing approach and the embodied approach and so on. Now, within these, and they might be slightly loose definitions, eventually what happens is that, say, for example, once there was this discovery of latent maps by these rats, it started becoming less and less compatible, less and less reconcilable with the idea that behavior is just stimulus response associations, that there is nothing called mind, and there is no merit in talking about unobservable mental phenomena. Now, Let's take some examples of scientific revolutions. For example, the Copernican revolution was something that was very significant, which basically replaced this idea of geocentrism, that Earth is the center of the planetary system, with this idea of heliocentrism, which basically said that not Earth but Sun is the center of this planetary system, which was basically then called the solar system. Now, when scientific revolutions do take place, it could seem as if the entire backbone of a discipline has been shifted or replaced. Newer findings start coming in, newer topics basically become more relevant, and older topics lose their sheen, and people lose interest in older investigations because they seem misguided, and there seems to be little value in pursuing those lines of inquiry. Now, eventually then what will happen is that once a new paradigm is set, people start offering theories within this new framework, and the same process of offering a theory, testing its predictions, testing the tenacity of the theory, and so on progresses. So once the paradigm shift has gone through, this new paradigm would take over, and it will form the foundation against which new research will be conducted. The situation will return to normal, and things will proceed within the ambit of this new paradigm, until the point that this same paradigm again needs to be replaced by the emergence of newer and more irreconcilable findings. All right, so this is broadly what I wanted to talk about. We are basically charting the progress of scientific thought from the positivist movement, a little bit about how theories are generated, what are broadly paradigms, and then we'll move on to more specific questions about, is psychology a science? How does psychology relate to theories and paradigms? What kind of inquiries do we undertake in psychology, and so on? And eventually then we'll start talking more specifically about the experimental method in psychology. Thank you.